There's the equation of the regression line for the temperature and cricket chirps example from Chapter 2. That regression line is sample-based, and we have numerical values for the slope and intercept. Those are both point estimates. The 0.23 is the sample-based slope, the 37.7 is the sample-based intercept, and those are point estimates for the population slope and population intercept. The main thing on this slide is really the notation. Beta 0 and beta 1 are respectively the population intercept and population slope, where if you look down toward the bottom of the slide, lowercase b0 and lowercase b1 are the sample-based intercept and sample-based slope. So b0 is a point estimate for beta 0 and b1 is a point estimate for beta 1. The other stuff, like the population-based random error that's at the end of that larger equation toward the top half of the screen, don't worry about that. That's stuff that we don't really need to deal with. It's true, but we don't need it. The main thing on this slide is really just the notation. There are 4 conditions for inference for linear regression, written in decreasing order of importance. So the most important is linearity, that you have a scatter plot that looks linear to begin with, then independence, then equal spread / equal variance, and then the normality of errors or residuals. The 2 that we're really going to focus on are number 1 and number 3, but I have things in here for all 4. The linearity condition is the most important, and it's the easiest to check, because all you need is the scatter plot of y versus x. As long as the scatter plot looks linear, or really as long as it doesn't look obviously curved, then that's good enough. The independence condition isn't covered in our book, but for completeness' sake I'll run through it. It's taken care of as long as there's some kind of randomization, either a randomly selected sample or experimental treatments being randomly assigned. Anything where there's randomization, that's going to take care of the independence. If it's not something where there's randomization, which largely would mean if you have a time series, then you want to check the plot of the residuals versus time and look for clumps. Basically what you would want to see in that plot is no pattern whatsoever, but if you have a bunch of positive residuals clumped together somewhere and a bunch of negative residuals clumped together somewhere else, that's a problem. That's when you have data where the individuals aren't independent of each other, and that's where the independence condition would fail. The equal spread or equal variance condition, this is satisfied as long as the variability of y looks consistent for all values of x. You can just use the scatter plot to check it, although you could use other stuff if you wanted to. The residuals versus x would work, or the residuals versus the predicted y values, since the predicted y values are a linear function of the x values. Those things would work, but it's probably easier just to use the scatter plot. The thing that you don't want to see, like it says at the bottom, a fan or cone shape, if it's going to fail, that's the way that it's going to fail. You get the fan or cone shape if, as the x values increase, there's more variability with the y values. With these 2 scatter plots, the one that you want is on the left. That one exhibits equal variance. If you go up that line from left to right, it looks like the y values are roughly equally spread out. The scatter plot on the right, that's the fan or cone shape, because as you go from left to right, as the x values get bigger, the y values are fanning out, the spread of the y values is increasing. That's specifically the thing that you really don't want to see here. Normality of errors or normality of residuals. If the sample size is large enough to apply the central limit theorem, so just like with means, a sample size of at least 30 would be what we'd consider to be large enough here. If that's taken care of, then this condition is taken care of. Or if the sample size is less than 30, but the distribution of errors or residuals appears to be normal, so symmetric with a single peak and no outliers, which you could check using a histogram, or you could check it using something called a normal probability plot. The normal probability plot isn't referenced in our book, but a lot of software packages make it very easy to construct them, and they're easy to read. What you want to see is that you want it to be straight. The one on the left is ideal, the one on the right is not. If a normal probability plot is not straight, it's typically something like the one on the right, where there's that elbow or bend in the graph. That's usually the way that it messes up, if it's going to mess up. This picture is supposed to represent the conditions for regression inference being satisfied, although really you can't see independence being satisfied in the picture. You can see the other 3. Linearity is satisfied because those little sideways bell curves are perfectly lined up. That orange line is going right through the axis at the center of the distribution in all 5 of them. Equal variance is satisfied because those little bell curves are all the same width. If you turn them counterclockwise 90 degrees, they would all have the same width. That's the way that that's represented there. And then the third thing that's represented there is the normality of residuals or normality of errors because they're bell-shaped curves. Like I said a minute ago, the ones that you really have to look for are just linearity and equal spread / equal variance. If you look at those 3 scatter plots, the one on the left is what you want. That looks linear, and going left to right, it looks like the spread of the y value stays pretty consistent. The one in the middle has a problem. It's nonlinear. It does look like the equal variance condition is satisfied there, but it is nonlinear. And the one on the right, the equal variance condition fails, because if you go from left to right, the scatter plot is fanning out, the spread of the y values is increasing, so the equal variance condition is failing there. When the conditions for inference are met, you can find a confidence interval for beta 1. B1, the sample-based slope, would be the natural point estimate. You would use a critical value from a t-distribution, although it's n-2 degrees of freedom this time, not n-1, and then multiply by the standard error. What typically happens is that you'll have software output where B1 and the standard error will be right in it. You just have to know where they are, and then all you really have to go get is the critical value. But first, why is the degrees of freedom n-2, not n-1? Well, if you think about the standard error that we would have for a confidence interval for a single mean, where it's s divided by the square root of n. That standard error is based on one sample standard deviation, since there's an s in that formula, and we lose 1 degree of freedom. If you think about it as you start with n degrees of freedom, and then you lose degrees of freedom from there. We have one sample standard deviation in that standard error. We lose 1 degree of freedom. We end up with n-1. Here, if you look at the standard error of B1, there are 2 sample standard deviations in there. There's the standard deviation of the x values in the denominator, and there's the standard deviation of the residuals in the numerator. So we have 2 sample standard deviations in the standard error computation, so we lose 2 degrees of freedom, and we end up with n-2. That's not a thing that you really need to know as far as the test is concerned or the homework assignments or labs toward the end of the course. I just figured I would put that in there so it didn't feel like that degrees of freedom change was something arbitrary. Here's the sort of software output that you'll have for a regression model. The yellow one is what you would get using R, although for now it might be better to focus on the one that says lab format toward the bottom, because there is a question on the lab that uses that exact formatting. The general formatting is the same for both of them, but it just seemed like it was a little easier to read in the lab format. In the part that looks like a table, you have 2 rows. You have an intercept row and a slope row. The intercept row starts with the word intercept, and the slope row starts with the explanatory variable, which in the case of the temperature and cricket chirps example was cricket chirps, or here just chirps. In the coefficient column, that's where you have the slope and intercept. By algebraic definition, the slope is the coefficient of x. So here it would be the coefficient of chirps. So the slope, B1, is 0.2307, and the intercept, B0, is 37.6786. That's what's in the coefficient column generally. You have B0 and B1. So if you need to get the equation of a regression line, those are the 2 pieces that you're going to need. The next column, where it says standard error of coefficient, the 1.9782, since that's in the intercept row, that's the standard error of B0. We're not really ever going to use that. Underneath that, the 0.0142, that's the standard error of B1. That's the standard error of the slope. You need that to get the confidence interval for the slope. The next thing, the t-ratio, that's a test statistic, and we'll get to that hypothesis test in a little bit. The p-value, that last column, goes along with that. On the bottom, where it says s equals 1.528, S is the standard deviation of the residuals. You'll never need to use that for anything, but that's always there in the output. And then R squared is what it was at the end of section 2.6. It's going to tell you the percentage of variability in the y variable that's explained by the regression model. Now that we know how the output is arranged, we should be able to get a confidence interval for beta 1. The only thing we really have to go and get is the critical value. If you go back toward the very beginning of the notes for this section, there are 7 nights where we have measurements for temperature and number of cricket chirps per minute. So n is 7, and for a confidence interval for the slope, the t-distribution that we need to use to get the critical value is one with n minus 2 degrees of freedom. So if n is 7, n minus 2 is 5. That's why we're using 5 degrees of freedom. So you'd want to use a t-distribution with 5 degrees of freedom and 0.95 in the central region, since it's a 95% confidence interval, and we get a critical value of 2.571. The other 2 numbers that we need, B1 and then the standard error of B1, those come out of the output, and they're both going to be in the slope row. So you want to be in the row that starts with chirps. In the coefficient column, that's where you get the B1, and then in the standard error column, that's where you get the standard error. Then the computation isn't too bad. You sub those 3 numbers in, multiply the critical value and standard error together, then you can do the plus or minus, and you end up with those endpoints at the bottom of the screen. A hypothesis test for the regression slope. These are the typical hypotheses, where really what you're doing here is looking for evidence of a non-zero slope, which would be the same thing as looking for evidence of some kind of linear association between the 2 variables. I suppose you could have a one-sided alternative if you wanted one, looking for evidence of a positive association or evidence of a negative association between the 2 variables, but that's not as typical as this. This is by far the most common scenario for the hypotheses, and this is the default setting for any kind of software. So the null should be beta 1 equals 0, which in words would be that the 2 variables x and y have no linear association. And then the alternative hypothesis is that beta 1 is not equal to 0, which in words would be that x and y have some kind of linear association. There is a common mistake with writing out the hypotheses symbolically, which is to have lowercase b's instead of betas, but it has to be betas because beta 1 is the population slope and the tests are always supposed to be about parameters. Having b1 instead of beta 1 would be like having x bar instead of mu. So just like with a test for a mean where you need to have mu's in the hypotheses, here you need to have beta 1s because beta 1 is the population measure. If the null hypothesis is that beta 1 equals 0, the test statistic ultimately ends up being b1 divided by the standard error, because the numerator would just be that point estimate b1 minus the value that's in the null hypothesis. And just like with confidence intervals, when you compute a p-value, you need to use a t-distribution with n minus 2 degrees of freedom. Back to the software, if you look at the one that says lab format toward the bottom, the thing that's labeled as t-ratio is the test statistic. 0.2307 divided by 0.0142 is 16.210. The same thing is going on in the intercept row, where 37.6786 divided by 1.9782 is 19.047. So the same thing is going on up there, but we're not typically interested in the intercept that much. We're much more interested in the slope. So t-ratio is the test statistic, and then the p-value would be the p-value for that test that was stated earlier, a null of beta 1 equals 0 versus an alternative of beta 1 is not equal to 0. So it's the p-value for a test with a 2-sided alternative to see if there's evidence of a linear association between the 2 variables. And here, that p-value is very small. Since the test is about the regression slope, you just want to make sure that you get your p-value from the slope row. The slope row being the one that starts with the explanatory variable, which in this case is chirps, not the row that starts with intercept. The p-value from the slope row is very small. It's listed in the table as 1.63 e negative 5, which is the way that a lot of software writes scientific notation. 1.63 e negative 5 is the same thing as 1.63 times 10 to the negative 5th, or written without scientific notation, 0.0000163. No matter what your alpha is, you're going to reject the null there. Any conventional alpha, 0.05, 0.1, 0.01, the p-value is far smaller than that. With a p-value that small, there is very strong evidence of a linear association between the 2 variables, the number of cricket chirps per minute and temperature. Lastly, you can do a hypothesis test for correlation, and our book kind of makes a big deal about it, but really, as long as you know how to do a hypothesis test for slope, then this is essentially covered. Because for any sample, the test statistic and p-value that you would get for a hypothesis test for the correlation would be identical to what you would get in the hypothesis test for the slope. The test statistic is there in that second bullet point, but it's exactly the same thing as B1 divided by the standard error of B1. You'll get the same number. To show that algebraically is quite a bit of work, but that is true.